Welcome to my presentation. I'm Sawan Khan from Tokyo University of Science in Japan. Today, I have a great pleasure to share my recent work on multi-junction photocatalysts of anatase, bronzite, titanium, and carbon dot, and their utilization for photocatalytic hydrogen generation. This presentation will cover a short research work on how to produce this kind of multi-junction in a feasible way. Let me start with the introduction to bronzite titanium. I guess everyone here already know clearly about rutiles and another phase of titanium dioxide. They are well-known photocatalysts in terms of both stability and also activities. However, titanium dioxide also have metastable phase such as bronzite and bronchite. I guess because of difficulty in synthesis of pure phase, this metastable phase show least interest so far. Typically, bronzite titanius, although they have a similar feature with well-known crystalli of rutiles and anatase. Let me introduce about the important features of bronzite titanius. They have monoclinic structures. They have band gap similar to rutile and anatase. Right now, we can synthesis of this material where hydrothermal sol gels and bronzite titaniums have a low-density crystal framework and large canal and void. This feature is very important in energy storage application. Beta titanium also show it great promises in photocatalysis. It was reported that photocatalysis of CO2 reduction performed by B-phase titanium show greater activity than a well-known anatase. Construction of heterojunction between anatase and B phase have been reported as an exceptional photocatalyst over the pure phases. In ideal band alignment between B phase and anatase allows both electron and hole transfer from anatase to B phase, and as a result, the electron and hole effectively separated, which further utilized for photocatalysis. And of course, this structure has been shown it great attention and a great interest for further research. Recently, there are many research already proceeded on the different kinds of heterojunction. For example, anatase rutile B phase, also silver oxide anatase B phase. So far, the mechanistic study of energy transfer within these heterostructures has been clearly studied and well understood. So the current trends of research is on how to produce this kind of material in a simple way. Until now, multi-process has been generally used to produce this kind of structures. However, this kind of multi-process may not be preferred for the industrial because of the complexity. So there is a simple way to produce the B phase and anatase heterojunction by just simple annealing. Because B phase is not stable, so when we anneal at high temperatures, B phase will transfer to anatase. Well, the problem is that multi-step process and high consumption by annealing might not prefer for the industrials. So the objective of this research is to produce a B phase heterostructure by a one-part process. Let me introduce our approach to produce B phase and anatase heterostructure materials by a one-part process using thermal method. You can have only two chemicals to produce this kind of structure by titanium chloride and ethylene glycol. By control the reaction temperatures and reaction duration, you will get anatase and B phase heterostructures without any post-treatment. This is the crystal structure of synthesized materials at 24-hour reaction time with different reaction temperature from 150 to 200. We can see that low temperature 150, 60, and 70, the dominant phase are bronzite, while the increase of temperature to 180, 190, and 200, So anatas are dominant, especially at high temperature 9 from 190, only anatas was appears. Also, this magnify XRD at a short range, we can see the broad peak, which is composed of B phase and anatas, and the peak is shaped to high angle due to the coexistence of anatas phase. To confirm this phase, Raman spectra were also utilized. As you can see, the broad peak here it shows about the composite between A and B phase. So from the XRD and Raman spectra, we can conclude that at low temperatures, 150 and 160, only B phase was formed, while at 170 to 180, the composite between anatas and B phase titania formed. However, at high temperature greater than 180, only anatas was detected. So next, we study on the effect of duration of reaction. Whether at longer reaction time, is there any change of the crystal structure? Well, at low temperatures, 150 to 170, almost no change, even though we increase the reaction time to 36 hours. However, at high temperatures, we can see that at 512, the pure B phase was observed, but from 24 hours, the anatas phase was increased significantly, especially at 36 hours, only anatas phase was appear. So from this result, we can conclude that B phase preferentially form at lower temperatures. In our experiment, B phase start transforming to anatas at temperature 170. More interestingly, beside the phase change, the colors of crude solution also change different colors. As we can see in the camera image, so when we increase the temperatures from 150 to 200, the solution start become brown to a dark black. So when I drop this solution into water and check under UV light, we can see a green and emitting colors. And at low temperature, 150, although I increase reaction time up to 36 hours, almost no any emitting colors were observed. But at high temperature, especially at 180, so the dark colors is enhanced when we elongate the reaction time. So almost no any emitting at 5 hour, but after 12 we can see clearly that the green emitting start observe. We wonder what the emitting is come from. So we observe luminescent spectra. So at different excitation wavelengths from 300 to 450 nanometers. So we can see a broad emittings at a visible range from 400 to around 600 nanometers. So this emitting is a unique characteristic of carbon dot, which enable to absorb broad light and also emit in the broad spectrum in the visible range. So there is no emitting for anatas, but a small emitting for the our materials on the side at 170. It have very strong emitting only carbon dot. And of course, they also have similar trend with the near-infrared excitations. So with these crystallizations, we believe that at high temperature and longer reaction times, ethylene glycol will decompose to carbon dot at the same time with the formation of anatas. As a result, at 170 degrees Celsius, we can get a composite structure of anatas, PFAS, and carbon dot. This is the morphology and nanostructures of our synthesized material. At low temperature synthesis, almost identical structures were observed at 150, 160, and 170, and start from 180, small particulate structure was formed, especially from 190, only particulate structure was observed. By TM image, we can see clearly that at low temperatures, composed of pure B phase was a nanosheet structure. At water 70, we compose of both nanosheet and particulate, while at highest temperature from water 80, almost particulate structure was observed by TM. By using high resolution TM imaging, we can see that our material composed of both anatase compound dot and B phase. This is the optical property of our synthesized material at different temperatures. We can see clearly that when we increase the reaction temperatures, the redshift of UV absorption spectrum was observed. So the redshift should be due to the coexistence of small bandgap on anatase structures. As we can see, these anatase have smaller bandgap, while that the Taylor's absorption at the visible to near infra should be due to the carbon dot, which is observed only with the sample synthesized at high temperature from 170. Next, we evaluate our material's photocatalytic property by hydrogen generation reaction under broad light from UV to visible, and ethylene glycol was used as whole scavengers. So we can see clearly that the composite material of B phase anatase and compound show the highest hydrogen production rate. We extend our work by loading with nanobond metals to increase the hydrogen production, while we loaded with nickel, cobalt, and copper. So by loading with this nanobond metal, hydrogen production was significantly increased by almost 3 times with nickel loading and 3.6 with cobalt and copper loading. And our material was also highly stable. We ran recycling experiment until 4 recycle tests and almost no change of the hydrogen production rate. So let me summarize what I have done so far. In thermal method, we enable to produce pure B phase. We also enable to produce multi-component of anatase B phase and compound dot and the composite structure of pure anatase and compound dot by controlling the reaction time and reaction temperatures. So the multi-component of catalyst show highest photocatalyst reaction for hydrogen generation due to the effective charge separation of anatase B phase heterojunction and anatase B phase compound dot. Thank you so much for your attention. Please let me know if you have any question.